Let us see about electric flux. The number of lines of force passing through some surface held in electric field. So we know the electric field lines. So how many such lines of force are passing through a surface? That is called electric flux. Scalar product of E dot dA is electric flux. So generally, how do we write the expression for electric flux? That is E dot dA. That is scalar product or dot product. Okay, E is electric field, dA is area. So this is phi E equals to integral E dot dA. So this is how we write it. It is an integral form. Okay, so it is electric field, it is area. What is the direction of area vector? Perpendicular to the plane along outward, drawn normal to the area. If suppose this is the area, it's like a disc which is on the surface. Okay, which is lying in the surface of a floor or something. Then what will be the direction of its area? It will be perpendicularly. It is perpendicular to the plane. So this is the plane. Okay, so it is perpendicular to this plane and it is along outward direction, so it will be in the outward direction. Yes, it is drawn normal to the area. That is the direction of area vector. So it not only for this case, for any case if you take, the area vector will be perpendicular to the plane and be outwards. Now we'll see about the special cases. So we have seen phi equals to E dot dA. So it is a dot product, so it means it is EA cos theta, where theta is the angle between electric field and the area vector. Okay, here what are we considering? E dot A. So it's like phi equals to E dot A. That means uh, we have to consider the angle between electric field and area vector. So first case, so here plane surface is normal to the electric field. So our electric field is like this and plane surface is normal to the electric field, meaning it is perpendicular to the electric field. And what will be the area vector? What is the direction of area vector? It is, yes, it is perpendicular to the plane, so it will be like this. Okay, and it is outward, so it may be in this direction or it may be in this direction. Okay, here we can take it in this direction itself. Okay, so what is phi? Phi equals to EA cos theta. What is theta here? It is angle between area vector and electric field. It is 0. So cos 0. So phi equals to EA. So this is the maximum amount of flux. Okay, because cos 0 is 1 and that is the maximum value of cos theta. So when there will be a maximum amount of flux, when plane surface is normal to the electric field, or when the area is normal to the electric field. So if plane surface is parallel to the electric field, then the case is different. So this is our plane surface and it is kept in the same plane as that of electric field. So electric field is like this. Many electric field lines are like this. Okay, and our plane surface is just kept like this. Okay, it is not perpendicular to the electric field, it is in the plane of electric field. So phi equals to EA cos 90. Why it is cos 90? If this is the plane surface, then what will be the direction of area vector? It will be outward, so it is like this, which is perpendicular to the electric field. The area vector is perpendicular to the direction of electric field, so the angle made by the area vector and electric field is 90 degrees. So EA cos 90 will be 0. So when plane surface is parallel to the electric field, the flux passing is 0. So please note that. So phi equals to EA cos theta. Let us write the units. So for electric field it is Newton per coulomb. For area it is meter square. So it is Newton meter square per coulomb. So yes, we also have seen VE equals to dV by dr. So instead of that we can write volt per meter into meter square. So another unit is volt into meter. And this is C. We are going to write the dimensional formula. For Newton it is mlt power minus 2. For coulomb, that is for charge, it is I into T, that is A into T. And for meter square it is L square, so ml cube T power minus 3 A power minus 1. So this is the dimensional formula for flux, electric flux. Now let us see about Gauss theorem. Electric flux phi E through any closed surface is equal to 1 by epsilon naught times the net charge Q enclosed by the surface. So what does it say? If there is a charge and it is enclosed by some closed surface, then what is the total flux passing through the surface? That is equals to 1 by epsilon naught times the net charge which is enclosed by that surface. So that is what is given. So we already know E dot dA, that is integral E dot dA is one formula for phi, that is electric flux. We are getting another formula, that is Q into 1 by epsilon naught, that is 1 by epsilon naught times the Q. Yes, so now let us see an example. So here we have a closed surface, okay, and inside the closed surface we have charges plus 1 plus q1 plus q2 plus q3 and minus q4 and minus q5 and all those charges we have. Now yes, now what is the flux here? Flux is equals to 1 by epsilon naught times the total charge. Now what is the total charge? Just add the charges, because charges are a scalar quantity, so you can just add it. So it is q1 plus q2 plus q3 minus q4 minus q5. So it is like sigma q by epsilon naught. So this is the algebraic sum of all charges enclosed by the closed surface. Please remember, it is closed surface. If the same charge is present outside, then you should not consider the charge. Okay, please remember that. Yes, yes, this is what I have told. If this is the closed surface and our charge is outside the closed surface, that is plus q is outside the closed surface, then what is the flux because of that charge through the surface? It is zero, because Gauss law says the charge should be inside the enclosed surface. Here it is outside the enclosed surface, so there will not be any flux due to the charge which is outside that. So here let us see some more important points about Gauss law. It is applied for any enclosed surface, no matter what is the shape or size. Okay, whatever may be the shape or size, Gauss law is applicable, and flux depends only on the net charge enclosed by the surface. It does not depend upon the position of charge or distribution of charge inside the surface. So we just want the information of the net charge. Okay, we don't want the actual distribution or something like that. It is not necessary. We are just interested only in finding the net charge enclosed by the surface. We should know phi, that is electric flux, that is inversely proportional to k, where k here is the dielectric constant of the material. This may you may use in some questions. Net electric flux through a closed surface due to charge outside the surface is zero. We have seen this point. Because of a charge present outside the surface, the electric flux through that in that surface is zero. So here we have just taken the conclusions of some cases. So here these cases are by using Gauss theorem. We have just found the electric field because of this infinite line of charge, infinite plane sheet of charge. And let us see only the result. That is good for us to solve the numerical problems. So here we have an infinite line of charge. Okay, so there is a infinite line of charge. It is continuing this way also, in this way also it is continuing. And to find an electric field at a distance d from this line, what is the expression? That is E equals to 2k lambda by d. So here k is 9 into 10 power 9. Okay, that value you please use, or 1 by 4 pi epsilon naught. That is what is k here. And E and d, what is the graph between E and D, that is electric field and the distance? It is inversely proportional, so it is like this. And what is lambda here? Yes, we should talk about the lambda also. It is linear charge density. So we already know density equals to mass by volume. So yes, that is volume density. That is mass by volume is volume density. If we want linear charge density, so then we have to take, it is Q by L. So if we want areal charge density, then we write Q by A. So if we want volumetric, then Q by V. So yes, that is what is actually lambda. So lambda here it means it is linear charge density. So please note that it is Q by L. Now let us see what is the case of an infinite plane sheet of charge. Now let us see about infinite plane sheet of charge. So previously we have imagined an infinite line of charge. Here you can imagine an infinite plane sheet of charge. Okay, and this is an infinite sheet. Then what is the electric field at certain at certain point it is E equals to sigma by 2 epsilon naught. What is sigma here? It is areal charge density. Okay, we have used the term lambda for linear charge density and sigma for areal charge density. So that is Q by A, because we are finding areal charge density, so use area. So it is sigma by 2 epsilon naught. And if we see in this formula, we don't have d or distance, no mention of distance is there. So the graph between electric field and distance is a straight line, that is it is independent of a distance. So electric field at certain point is independent of distance, so it appears as if like it is like this. But this result, that is independent of distance, is strictly true for the points lying in the neighborhood of this sheet. Okay, please remember that point also.